Unit 4 of AP Physics, Electricity and Magnetism is all about magnetic fields. And so this video will introduce you to what a magnetic field is and the force that it exerts on a moving charge. We'll start by defining magnetic field. For starters, the magnetic force is a field force. We know several other field forces, such as the gravitational force and the electric force. And just for a refresher, something as a field force indicates that there must be a field or a region where that force is felt, because you don't have to have contact if it's a field force. So a magnetic field would be a region where a moving charged particle may experience a magnetic force. The symbol for magnetic fields is a capital letter B, and you'll notice there's a vector symbol on top indicating that a magnetic field has a direction, just like a gravitational field or an electric field. And finally, the units that we use for a magnetic field are Teslas. We'll talk more as we get to equations about what exactly a Tesla is, but it is named after the famous physicist Nikola Tesla. And typically we work in milliteslas or microteslas. So kind of like a capacitance, a Tesla is a rather large unit. The majority of this video will focus on charges that are moving through magnetic fields. So one of the statements that was on the previous slide talked about how a moving charged particle in a magnetic field may experience a magnetic force. Notice that word may in there. I didn't say that it will experience a magnetic force, but it could possibly experience a magnetic force. And to understand why that word may is in there, let's take a look at the equation for the magnetic force on a moving charged particle. This equation does appear on your equation sheet, so it's something we'll be able to use, and we'll use quite a bit. You'll see that the magnetic force, that F sub capital M, is equal to the charge times the charge's velocity, and then there's this cross product in there. And so the charge times the object's velocity crossed with the magnetic field. So taking a look at this equation may help us better understand why that word may is in there. For starters, for there to be a magnetic force, we need our particle to be charged, and it has to be moving. So Q and V both cannot be zero. Additionally, since there's a cross product in there, it is entirely possible that we have a charged particle moving in a magnetic field, but it doesn't experience a force. Think of when the cross product is equal to zero. If you think about it, that cross product is zero when the two objects are pointed in the same direction. So if the velocity, or opposite directions, so if the velocity is parallel to the magnetic field, then we will not have a magnetic force. Just a reminder, with cross product, you can use the magnitude of one vector times the magnitude of the second vector times the sine of the angle between them to find the magnitude. So in this case, that would be QVB sine theta. Remember that theta is the angle between the velocity and magnetic field vectors. And then we could use the right-hand rule to find the direction. A reminder about that right-hand rule: anytime we're using the cross product, our thumb represents the first vector, or the V in this case. Our first finger represents the second vector, or the B, and then our other three fingers would represent what that is equal to, so they would represent force in this case. One really important note here: that Q doesn't have absolute value signs around it. So if we have a negative charge, then we would want to plug in that negative sign for Q. As a result, when we're doing the cross product, when we're using the right-hand rule, if you have a negative charge, you want to make sure that your thumb points in the opposite direction of that charge's velocity to determine the direction of the force. Now, I have also heard people use their left hand when using negative charges. I don't necessarily recommend that, because I think that there's a lot of temptation then to always use your left hand. And we know it is called the right hand rule, so most of the time we should be using our right hand to use that right hand. But it is possible it will give you the correct result. Using that right hand rule will be a big thing on the AP test. we'll want to make sure that if you're given two of those vectors, you can predict the direction of the third. So not only knowing the direction of the force if you're given the velocity and the magnetic field, but also being able to like know the direction of the velocity if you're given the force and the magnetic field, or given the direction of the magnetic field if you know the velocity and the force. We'll do some practice with that. The last thing I wanted to talk about in this video is the path that a moving charge will take in a magnetic field. Because of the equation containing the cross product for magnetic force, the magnetic force must always be perpendicular to the velocity. Also, that magnetic force must always be perpendicular to magnetic field. That's what the cross product does. It gives us a vector that's perpendicular to the two vectors we are crossing. There are a few things that result from that. And to understand one of the results of that, I have an example field set up here. All these X's represent my magnetic field. Just for a reminder, when we have a three-dimensional vector, X's represent into the paper or into the computer screen in this case, and we would use a dot to represent out, as if you're looking at the tip of an arrow that's coming out toward you, or you're looking at the cross made by the tail vectors of an arrow going away from you. I also have a positively charged particle that is moving upward as it enters this magnetic field. So I want you to take a moment right now and pause the video, use the right hand rule to determine the direction of the force this particle would feel when it enters this field. You should have determined that the direction of that force would be pointed to the left. But we know that just because there's a force pointed to the left, it doesn't mean that my object is going to immediately move to the left. So if I were following the path of this particle as it moves upward, it'll start to curve a bit. And so as it curves, we now have this particle in this location approximately, and it's now moving in that general direction. So once again, I want you to pause the video and predict the direction of the force that this particle feels. You should have found the direction of that force to be the direction of this blue arrow right here. And again, noticing that the direction of the velocity and the force are perpendicular to each other. Once again, my object isn't going to move directly in that direction of the blue vector. Instead, it's going to kind of curve along here. It'll get to a point where its velocity is pointed toward the left. What's the direction of my force now? You should predict the direction of that force to be downward using the right hand rule. So my object is going to continue to curve in its path, getting to a point right here where its velocity vector looks something like this. With a velocity vector that looks like that, I would have a force vector that looks something like this, which then once again curves its path even more. And if I were describing the path of this particle, you may, provided that I actually drew this perfectly correctly, you may describe this as something like a semicircle. And therefore, the magnetic field, or sorry, the magnetic force in this case is acting as a centripetal force. Notice that all of my blue vectors are pointing toward the center of that circle. Any charged particle moving in a magnetic field is going to move in a circular path. That path may not be a complete circle. It could be a quarter of a circle, a half of a circle, 3/4 of a circle, or anywhere in between, depending on how far that magnetic field extends. But we can use our knowledge of circular path and circular motion and centripetal force as we are analyzing the path of a moving charged particle in a magnetic field. One last comment that has to do with the fact that the magnetic force is perpendicular to velocity. That also means that magnetic force cannot do work. Think about our definition of work. Two ways we defined it. One of those ways being that work is a transfer of energy from one thing to another. And the only energy we'd be talking about here would be kinetic energy. So if you think about kinetic energy, that's talking about the speed. And since my force is always perpendicular to my velocity vector here, it cannot possibly change this object's speed. It can only change my particle's direction of its velocity. Another way that we talked about work was by saying that work was equal to the integral of F dot dr. Think of what you know about the dot product. That dot product relies on the cosine function. And that would be the cosine of the angle between my force vector and kind of a small displacement vector showing the direction that the particle is moving at that point in time. If you think about the direction between those two, it's going to be 90 degrees. And the cosine of 90 degrees is always 0. There's another reason to understand how the magnetic force cannot possibly do work on a charged particle.